Thank you. While my slide is pulling up, I am a research scientist from North Carolina State University. Thank you. When I saw the final program, I feel I'm quite out of place for the presentation when a lot of them are talking about equity and inclusion in a lot of those conversations where I want to specifically talking about projects that we've been working on, I think fits into the large word of the theme of the symposium, which is looking at opportunities, how machine learning can be used in practice to address some of the issues that we have in terms of environmental monitoring and for applications that improve our monitoring of the climate conditions. If you can move into the full screen. Right. Okay, thanks. So I guess I'm going to start with the topic of climate change, and I think this it's a depressing topic, but it's things that's real and happening. And this is the newly released State of Climate report from World Meteorological Organization that was just released in March and shows the actual increase of temperature from the observations we have going back to the late 1800s. And we actually monitoring the climate or the weather conditions much longer than that. If you go back to National Archive, you can actually find the temperature measurements done by Thomas Jefferson in his diary during the time when they signed the Declaration of Independence in Philadelphia. So you can actually figure out what the temperature it was in Philadelphia at that time. But because since the 1800s, we have much more reliable measurements across the world so that we can have more confidence on how we can use them for monitoring at the global level. However, those are actually done by the station measurements that you have seen on this map, where you have a lot of station measurements across different parts of the world. But one thing probably jumping into your mind is that why there are so many gaps in certain parts of the world. That is because we don't have measurements in those areas. So you see we have really high density of station measurements in North America, parts of the coastal part of South America. Europe has a lot of station measurements. But if you look at other parts like Africa, the continents of Africa and the central parts of Asia, where you have a lot of regions that you barely have any station measurements in those cases. So during my dissertation research about 7 years ago, what we had found is that if you rely on those station measurements that unevenly distributed across the world, when you do those climate analysis, specifically looking at the impact at local and regional scale, that can lead much larger uncertainty. Even though with those stations, you can get really good high confidence monitoring at the global level. But when you go to local, you look at impact, that can still have larger uncertainty, which can cause issues with planning and policy making related to the local level actions. And to be a little bit more, this plot is really big on the screen. Looking at more details, also looking at stations across the world, where in Europe, in North America, you have less missing values in those data measurements from stations, where in other parts of the world, you actually see higher percentage of missing values. So that also causes quality issues when you're using those station observations for the climate monitoring and impacts studies and that. So the idea that we a lot of times when you're trying to do climate monitoring and impact study with those sparse station networks, is that you try to generate spatially complete data sets from based on observation. You look on the left and trying to get something on the right. And so different ways people are trying to do is that having specifically focus on region where you have high density station network, that gives you a high confidence of generating those graded data set. For example, in North America, in Europe, you have multiple different data sets based on those observations because it's easy to do. You have a lot of high density stations. And sometimes people were just coursing it out, right? That we create a global data set, but at much coarser resolution that to ensure each grid or each area that we have at least one observation for us to do the monitoring. And then the other approach is that can we combine different sources of data to fill the gaps in the data that we don't have the station measurements, that oftentimes including the satellite remote sensing, including the model simulation, especially in the recent decades. And so the last one is a lot what my group had been working on recently on doing that. So specific ones I'm going to talk about here today is how can we create a model that in the regions where we have really high confidence with high density station measurements in North America, and then try to use transfer learning techniques to move this model to other parts of the world where we have limited station measurements, and then to create increase our confidence and reduce uncertainty in those regions. So this project specifically looking at, now we have the station measurements in North America, and then we have auxiliary data from remote sensing, from elevation and other parts, and then we have a high resolution graded temperature data set, a climate data set that created by different groups, and then we can create a deep learning model that either using convolutional neural networks or neural process or other types of models. And once we have that model developed and evaluated, we can combine the model with station observation over other regions, as well as auxiliary data that's available over other regions as well, to create high resolution data sets, not in, in other parts of the world. It's not just in North America anymore. So use that to create the data set to have higher confidence in those regions. So those are the data we have been using. So for those of you who are not in climate or environmental monitoring, we have daily station measurements across the entire globe. That's about 13,000 stations through the data exchange between different nations. And then we also have high resolution daily data set over the United States at 5 kilometer resolution scale. So that is created by NOAA, that has been used for the national climate assessment, as well as other types of the official climate monitoring for US. So that's an official product released by NOAA. And that would be our target when we're creating those deep learning model. So the two methods we have been testing, one is the impending algorithm that has been quite commonly used in computer vision, is that when you have those missing values in an image and you try to generate a guess for those regions where you don't have any existing data. The other one is more developed more recently. It's the neural process model. Is trying to use a neural network to approximate the Gaussian process, where the advantage of that model specifically is that you can actually generate the uncertainty of the output by itself. So that gives you a really interesting artifacts that to assessing the output of the model at the same time, right? So it's not just a one value of the guess of what the temperature or the precipitation may look like in that region, but also gives you an uncertainty of how confident you are in the output of that. So that is important because when you're trying to use that for a study of how its impact on the local communities, that can actually gives you you can use that as a way to decide whether you trust that data enough to derive the conclusion or not. Okay, those equations is less probably less important to many of you, but it's just those are different metrics we're using to evaluate the overall performance of the models. I know some of you may think that it's not its average score, so that it will or still need to look at some extreme cases and how it performs in those extreme events. For example, in tropical cyclones, in the hurricanes, how it performs as well. So we also did that evaluation for those cases as well. So here, just to give you a few of the examples showing how the model performed in the North America in this case. On the top left side, you will see the reference data set, which is the official graded data set produced by NOAA. And on the right side, it's the deep sensor, which is the neural process model, and estimates from the model for the annual mean for the 1995. And then on the bottom left, it shows the differences, spatial distribution of differences between those two. One's reference and one's estimates. And then you see the spatial pattern as overall consistent in the model output from deep sensors. However, you see there are differences in terms of temperature between the officially graded dataset and model outputs. But when you relate that to the uncertainty or standard error of the deep sensor model outputs, those are usually, when you have larger differences, those are usually the regions where we have really high diversity of terrains in the mountain regions, where, for example, you can see in the Rockies, as well as Sierra Nevada on the west side, but also in the Great Smoky area in the North Carolina and Virginia. That's where you see higher uncertainty on the bottom right figure in terms of spatial distribution. That gives you uncertainty of the model output itself. And when we're looking at the entire year, over the entire year, this is time series of the maximum temperature weighted over the entire United States. Lower 48 states, not the entire. Though we did not have Alaska and Hawaii in that case. And so this is time series where the blue line is the model estimation from the deep learning methods. And then the yellow line is the official records that NOAA keeps from the graded data sets. And the shaded blue area are the uncertainty estimation from the model itself. So you see both the reference and models follows the overall temporal pattern quite well. And also the uncertainty estimation gives you an idea of how confident we are about the data sets created by the deep learning model itself. And overall, we look at statistics of the root mean square errors and mean biases as well as other things. The number are quite low in those cases. And those are for temperature. So we can also look at precipitation, which are two important measures when we are looking at monitoring of the climate conditions. And then those are spatial pattern when we're comparing different results. One on the left columns, we have two other reference data sets from different groups. One is from the Oregon State University. The other one is from the Oak Ridge National Lab, the DayMat data sets. And on the top right is the NOAA data set that is the official record keeping. And then on the bottom right is the figures that we generated with the machine learning based methods. From this case, you can actually see the spatial pattern of the deep learning generated methods are quite blurry in the data itself, which we are trying to understand how those like sharpness of the image can be further improved with the limited observations that we currently have from the station measurements. And so one of the things we're trying to look at is change how the model is designed to maximize, to adjusting the objective function in terms looking at the spatial pattern by itself as well, not just the absolute value itself. So we are looking at those like differences in the continental United States, the lower 48 states, and also the uncertainty estimation for those parts. And we see the uncertainty mostly in a lower, leaning towards the lower end of the estimation, but we still have regions where you have large uncertainty, where those are also regions in the mountain terrains where it's very hard to get accurate measurements, estimation of the precipitation amounts over there. And like I mentioned, we also want to look at those extreme cases. And so these are one of the tropical storm Bill in the year 2015, looking at the top row, which are the official precipitation amounts from the graded data set that NOAA creates. And on the bottom row is the precipitation amounts that generated from the deep learning, deep sensor methods. If you try to follow the spatial pattern as the progression of the storm from the very beginning, the June 15th to very end until it moves into further inland in June 19th, overall, the spatial pattern evolved quite similarly from both observations and to the model estimation right there. There are some of the issues in the more inland area when we get to later parts of the storm. When you look at the eastern part of Texas at the end of the storm, that is we see some underestimation from those model outputs. So those are the things need to be further improved in that case. So when we're comparing with the station measurements that it shows in those like heavily precipitated areas that we actually do pretty well in terms of model estimation comparing to the station measurements. But in the regions where the storm are less intense, we actually see higher differences there, which is fascinating for us to further consider how we did the estimation in the high extreme events well, but not in those general cases, which is fascinating to consider in the further work there. So like I mentioned before, that we want to move this model to other parts of the world where we don't have a high resolution graded data set. And so here, just showing some of the examples we have been doing with Europe and then in Asia. With Europe, that we actually can compare with some other existing graded data set because they have high density resolution data sets. So we can compare with that. And based on we did not do any further fine tuning with the model that we have in North America and then directly apply it to Europe that can actually get quite well in terms of spatial pattern differences when compared directly between the left side, which is their official data sets for called EOPS, and then on the right side is the model, a deep learning model that we created in North America, directly apply to the data in Europe. And when we apply the same thing to Asia, the model performance, it captures overall spatial pattern. However, that in the regions like the Tibetan Plateau, and that is really extreme conditions, that is high elevation, complex terrain, that we do see the model does not perform well in the top of that plateau where the terrain is very complicated and there's no spatial observation above 5,000 meters in those cases, which are some things need to be further improved in the observation network by itself. And there you can also see a much wider spread of the uncertainty estimation in the part of Asia. So just to conclude, since I only have 2 minutes left, and so we do find that deep learning methods, in this case, neural process, can create the accurate estimation of the temperature and the climate conditions with those added standard error. That's an added benefits for us to understand the uncertainty of those data set by itself. And through those transfer learning methods, we can use the model we trained over North America to other parts of the world that to create those data set that currently doesn't exist. And then lastly, that we are going through more independent evaluation of the data set to further understand the uncertainty and how those can be useful and be relevant for this conversation. Thank you.
So the next section is, this is the Q&A session. So if you have any question.
I thought I can just move away so nobody asks questions.
Thank you for the talk. So how does the current U.S. administration impact the data collection efforts and also like your own research, the climate research in general?
That's an interesting question. So since the data, I was having this same conversation during lunch with some others when I was talking about my work. So currently, a lot of data we use are kept in official records, the data archive that NOAA has, National Centers for Environmental Information, which are by law required as an archive. So almost part of the National Archive. So it's not at risk, at least at this moment. For other parts of the data, there are a lot of those data actually have multiple copies. And so other parts of the world also keep the same copy or similar copy of those data sets. So I think those are fundamental records that very, I would say, robust, some of those data. And also there are also strong interest from the community trying to preserve those information by other parts of the world. And for my own research, and I think we haven't been heavily impacted at the moment with the existing funding that we have, but I think people are concerned. That's a fair statement, I would say.
Excellent presentation, by the way. During your presentation, when you showed the grid, I thought part of the idea for the new system is to sort of fill in information that's missing. But when I look at the image, I saw some portions of your map that had missing details. Was that intentional, or was that not intentional? So if you could go back to, I think, slide number 6 or slide number 7.
Okay, let me,
Right.
if you can go click on this slide. This one?
Yeah, so you can see that, look down in Florida. And again, if you sort of move forward again, about 4 more slides. Go forward. No,
I'll
backwards.
go forward. Okay.
Yeah.
Is it this one?
One more.
One more? Okay.
One more.
One more.
I lied to you. One more.
One more.
Okay, so you can see, I think it's like maybe a lakes or something. Look in the middle of the. There you go. Was that intentional?
This is not in. Okay, I need to. My neck is hurting. And so those are, so these are differences. Are you talking about this one or that one? Oh, this is not intentional. This is actually because this one is from the reference data sets, and this one is the estimates from the model. So that we are trying to compare this one to the left one. So this gives you the difference between those two maps right here. And then we do see there are some details that are missing in those model output by itself. And so we want to further improve the model performance by how can we better capture the spatial patterns in it. So one way we are trying to do is to redesign the objective function, the model try to minimize that, including the spatial patterns by itself as well.